without further ado, I'd like to introduce our speaker, Mr. Don McPherson of Hydrodynamic. Brings you such programs as PropCAD and NavCad, and he's going to speak to us about lower order modeling tonight. And I guess with that, I'll let you take it over.
Thank you. Okay. For the benefit of the folks on the web meeting side of things, I'm going to work with a microphone. I tend to wander a little bit, so warn me if I get to the end of my cord here. Thanks to the folks in the room for coming out tonight on such a typically New England evening. Just a real quick summary about us. I'm with Hydrocomp. I was one of the founding partners in that with Jill Aaron. We've been at this game a long time. Hard to believe it's been 1984. I'm the technical director with Hydrocomp, also a few years back elected as a SNAME fellow. What we do at Hydrocomp is we're a small engineering research company. Commercial software is most what we're known for. Dave, you mentioned PropCAD and NavCad, but we have a variety of other things that we're involved in as well. Of course, with that software, we have an active consulting service business. And a part of it also includes training and professional development, not just in software side of things, but we do an awful lot of work with kind of the second-tier propeller manufacturing community, where we'll do professional development on propeller design or manufacturing techniques, inspection, things in that domain. So for today, what we're going to talk about here is the use of what I term as lower order tools. And I want to sort of use that as a distinction, not in a derogatory way. Lower order tools can be immensely powerful and absolutely required as a part of the design process, and we'll see about that here. We'll talk about computational models and what we call proper order, and the order in lower order, higher order. You'll begin to understand that as we go through this here. Now, my world is about hydrodynamic and propulsion system simulation, and I underline system because that includes many different aspects of it. And conceptually, we want to move away from thinking about optimization from individual components and thinking about what's best for the system. Now, specifically, with the advent of CFD tools that are becoming much more efficient, workflow processes fit better into our design spiral, we still want to use lower order tools to enhance the capabilities and the capital investment that we make in our CFD assets. Specifically, kind of the topic is design space optimization, DSO, and initial design space optimization. But we'll talk about a variety of different lower order applications that connect with CFD. And the tools that we'll use here, just very briefly mention as examples, will be our NavCad software for the system simulation and our prop elements code, which is a wake-adapted propeller design tool for the propeller components. Now, the use of lower order tools with CFD, the justification for this really is threefold. We're going to see that there's financial benefits to using lower order tools, that the technical outcomes actually provide for better answers, and risk mitigation, greater confidence in the results. We'll see some case studies and real examples of that here toward the end. The roles of lower order tools in the context of CFD is about this system again, simulation of the system, the Hull-Propeller-Drive-Engine system. Narrowing the design space, when we flip the switch on CFD, we actually want to know that we're in the neighborhood. We don't want to be looking at places that are not going to prove useful. We want to be refining our answers with CFD after we already know the direction that we want to travel. Benchmarks for evaluating CFD results is an incredibly important part of the use of lower order tools, because CFD is an analytical simulation. It's a projection, it's weather forecasting. So we want to know that those projections are meaningful and reasonable and lower order tools can provide the benchmarks for that. And lastly, we can kind of cleverly use CFD results sparsely in conjunction with lower order tools to get a more broad understanding of the entire scope of the hydrodynamic and propulsion system. Now, the nature of marine design, because that's really what we're after here, is how do we best use these tools in the context of ship design, marine design. It's driven by more than hydrodynamics, much as I would prefer that everything is about flow and propellers and resistance and hydrodynamics. I fully acknowledge that we have things like safety of life at sea, we have cargo, we have structures, we have all of these things that are a part of the business-driven decisions. And that's this third item here. The meaningful design objectives that we have as a part of ship design are business-driven. We don't care that we have a slippery ship, a low-resistance ship, unless that in turn saves my owner money. That's the objective here. Fuel, regulatory issues like CO2 production, emissions, EEDI, some of these kinds of things that we're seeing is an important part of the business plan. We have to meet those regulatory requirements, but they have nothing to do about the optimization or the individual analytical setting. The meaningful design objectives are business decisions. And those business decisions are not about individual pieces, they're about the system. So the system model that we want to hit on, that I mentioned earlier, the Hull-Propeller-Drive-Engine system, is where this whole story has to start. Now, component optimization within that system, after we have the system, is valuable, of course. You know, we know that a reduction in resistance is going to lead to lower power, lower fuel consumption, better CO2 production. But we want to couple everything we do either directly or indirectly with a system simulation. Now, ship propulsion simulation, we're using our NavCad software as an example for this. The component constraints, this is kind of an extension of what I just said, that can also affect the system. I use the example of a propulsor noise. A lot of the work that we're doing this year has to do with underwater radiated noise and hydroacoustics. So we're making system decisions for the propulsor that have nothing to do with optimum efficiency or minimum fuel consumption. They're about signatures in underwater radiated noise for marine mammals. The NavCad software gives us the tool that provides that framework, that Hull-Propeller-Drive-Engine system framework. And you'll hear me say that time and time again, because that's really the anchor and the foundation upon which we build any discussion about marine performance prediction. Now, within that framework, we have resistance and hull-propulsor interaction. We have propulsor performance and system propulsion, meaning what's the engine going to do in order to drive the propulsor in order to meet the thrust that the hull demands. And then mission duty profile, we're more than just a single design point. We want to know for a search and rescue mission, for example, that has a period of loitering, it has a sprint requirement, it may have a towing requirement, what the total overall fuel consumption for that mission duty profile might be. And NavCad gives us this platform for what we're talking about here, this initial design space optimization. So let's step back and go to school. You've probably seen this called the design spiral. Now, there's quite a debate as to whether we as engineers actually function in a design spiral approach, but for the moment, let's just go with it. The design spiral is a way that we can characterize how designs evolve, that we start with the least precision and the greatest uncertainty, where we're speculatively trying to create a design. Well, we still have to think about all the different steps in each loop, requirements, major dimensions, cargo, powering, ship stability, equipment, all of these things we have to touch on. But as we then go through that first loop, we understand the problem much better. And then we can get more refined and more refined and more refined. So our task of evolution is always from lower precision to higher precision. When we start this design with a blank sheet of paper, we have no idea how long that ship is going to be. We may have a sense of what it might be, but we don't know what the final answer is. As our design matures, we understand it more and more. So that begs the question, when is the really important work completed that we do? If you take anything away today, there's a couple of quotes here, and I'll read this if I may. By the time of the first design review, performance, cost, and schedule will have been determined to the first order, because all of the critical assumptions and choices will have been made. The serious mistakes occur on the first day. Well, let's think about the questions that we actually answer on that first day. What kind of material are we going to build our go-fast boat out of? Is it going to be aluminum, or is it going to be GRP? Is it going to be steel? That influences a lot of things. What's our propulsion system going to be? Conventional shaft-driven propellers, water jets, surface drives? These are big major decision points that affect everything downstream. 50% of a product's life cycle costs are determined by the result of the project's first 5%. What I'm trying to do here is to really underscore the importance of initial modeling of the characteristics that you're trying to evaluate. That the really important decisions occur early in times when we don't know very much about what the answer is going to be. So this second bullet item here, proper model selection in early stage design is crucial if we want success in achieving our ultimate goals here. And I kind of use the term sweet spot for that combination of facility and precision. We don't have a lot of precision, but we need the ability to get answers that we need. Now, this is a great graphical example, a way to wrap your head around kind of the idea that I'm trying to propose here. One model that we deal with is a CAD model. Everything else we're going to talk about here are computational models. CFD is a computational model. But if we talk about a CAD model, we need to look at what's the purpose of our objective. This first graphic here on the left is what I believe is a 32,000 piece CAD model of an engine. You could go and build an engine from that. Would you use this in a CAD model for a ship design? Of course not. Its precision is way too high. It's of far too high in order to be useful for the purpose at hand. So now we actually developed a little utility to simplify CAD models from the very, very detailed component to finding an envelope, like in the second column, to actually creating what we call a prismatic element representation of a model, where all you need in that is the basic connection points. That's what you're after when you're doing ship design. You don't care about the internals of the engine. You want the connection points. You want those things. And so I forget what the order of file size was, but it was about 500% reduction of file size in order to be able to use this engine in a full ship design. So think about the purpose of the task before you try and capture the model. So let's talk about computational models, and we'll talk about equations here. An equation form can help us describe when I talk about an order, because it's very well defined. A lowest order might be a line, simple two components, y equals ax plus b, you've got a and b. As we increase the order of a polynomial up to a fourth order in this equation here, we can see how we have more precision, but we also have greater flexibility, greater movement. So which is better? Is a higher order always better than a lower order equation? Not necessarily. Most people would suggest that higher order, and if I do this in a room of big people or a large number of people, we'll actually get most people answering that higher order is better because it fits points better. Well, are you sure? And what I want to kind of describe for this is that we really need to have an underpinning of the relevant physics involved. That the points that were in our graphic right here, this is a line and a quadratic and a cubic fit through this small collection of points. And we don't know which one more faithfully reflects the physics involved until we know what the foundation of that physics might be. Now, it's also important to understand that what computational models do is they approximate the differential equations that describe the physics. And that comes down to this third bullet item. I forget who said this, and I've quoted it on a number of occasions, but it's a great quote. All models are wrong, but some are useful. And so what we're trying to do with these models is fit the most useful ones into our design setting. And I always use an example of a water jet impeller because it's a great one to describe how a very, very simple computational model, a cubic relationship between RPM and power, really higher order analysis offers nothing if our objective is performance, where we're looking for, if I spin an impeller at a particular RPM, how much power does it draw? Now, there actually is a slightly higher order of that. We can refine that with a boat speed correction, but that's really it. We don't have to go to extremely complex analyses on water jet impellers because they follow a pump rule very, very closely. Now, if our objective of analysis is to look at things like cavitation or design inflow so it better matches or integrates with the impeller, then of course we need higher order codes. But the nature of the problem, we have to find the problem, understand the problem to fit the order of the solution to that. So when we talk about hydrodynamic codes, which is the world that I particularly live in, is that we have two pieces of this. When we talk about a computational model, we have the data of the model and we have the prediction side of the model. And each of these has varying quantitative, qualitative strengths. Now, the image that you see here, and let me run this back, you'll see how what we're really looking for is the hole in the water when we're talking about hydrodynamic, big ship performance issues. And it's appropriate to evaluate or ask yourself a question: what's a reasonable outcome for this? And I wanted to share a couple plots with you here. When we're talking about finding greater precision in predictions and greater precision in answers, what's a reasonable expectation of this? This upper plot here is an effective power curve, functionally resistance, across speed of a number of different model tests of a ship called the Lucy Ashton. Now, if I can take just a quick sidebar, the Lucy Ashton is a great story. If you haven't learned about it, look it up. But it's an old side wheel paddle cruiser, or I think that's what they call it, that the British Ship Research Association, BSRA, tested in full scale in the early 1950s. And just how they were able to test it in full scale was really wicked awesome. They took Rolls-Royce jet engines and they mounted a load cell between that and the ship, and they ran it in order to find out what the full-scale drag was. That was really clever, really interesting. That alone is worth understanding. But then what they did is they went and took models of different scale that very, very accurately reflected the geometry, including the sagging of the hull that was tested at full scale. And this is a plot of different model scale lengths. And if you look at the plus minus error, it's 5%. So the best of the analysis that we could do in model testing in order to achieve full-scale outcomes, depending on ship length and Froude numbers and the characteristics between wave making, drag, et cetera, really was about 5%. So anything less than that, you have to question whether that's realistically optimistic or not. The lower one is from a set of propeller curves, KT, thrust, KQ, torque, and efficiency, for a study that was called the Potsdam Propeller Test Case, which is kind of a CFD benchmark that we all use to evaluate propeller codes. You'll see that the thrust curve is very tight, the efficiency curve less so, but the KQ curve, which is the torque curve, has a lot of scatter in it. And that is something that we see a lot because drag in hydrodynamic analysis is difficult. Lift is easy, drag is challenging. And so torque, the rotating drag, is a little more difficult to get. So now we're going to establish some order in different hull and propulsor kinds of options. And let's talk about resistance here. In the workflow process, and when we're talking about order, I use a term that wasn't my own creation, but one I co-opted from a CFD company, actually, was about 1D, 2D, 3D. And that 1D is a parametric analysis. And you can understand the 1D as a dimensional relationship by the kind of parameters that we use. Length is a single dimension. Beam, draft, volume, and the corresponding coefficients of that, like length over beam ratio, prismatic coefficient, characteristics of bulb or transom immersion. These are individual one-dimensional parameters that we use to describe a ship. Now, I can get more refined about the hole in the water by looking at the sectional area curve. That's a longitudinal distribution of shape. For a single prismatic coefficient, which is the integration of the sectional area curve, I can have any combination, an infinite number of sectional area curves. So that gives us an additional refinement of the volume. And for that volume, I can have an unknown number of surfaces that encompass that volume. So the highest order, CFD, is the 3D, slightly lower order, sectional area curve, 2D, and lowest order, parametric, 1D. And so the prediction methods for 1D is really completely empirical, that we look to systematic series or random data methods. Series 60 is a great example. Everybody in school studied Series 60. It uses parameters, fineness coefficient, prismatic, length over beam, beam over draft, etc. And then one of the things about if you're looking at a novel ship, it requires some user understanding or selection of which of the many different available empirical series we have to apply to our method. And we'll touch on this later, but you can also leverage higher order results with a parameter-based analysis for what we call an aligned prediction. We'll see that this is a fabulous way to leverage existing CFD assets that you've already run and apply that higher order precision back to your design using a lower order technique. The second level, 2D, volume-based, in our NavCad software, we have what we call the analytical distributed volume method. It's a linear code that uses the sectional area curve, the beam distribution, and the immersion of the section areas. And this kind of a code, a wave-making code, really is quantitatively very accurate. Again, it's not suitable for all ships, but again, we'll talk about that. And it can be used for things like predicting wave height, wave patterns, wave elevation patterns. As we get to the full 3D, CFD, of course, RANS codes, this is a big jump in order. We get the full surface. The interesting thing about CFD for us is it's the only method that really allows for observation of flow. So if we're looking for shed vortices, if we're looking for what I would refer to as hot spots, local velocity peaks and things like that, CFD is really the only way to get the precision necessary to use that. But It's not always the highest fidelity method. Let's take Series 60 as an example of that. If you were designing exactly a Series 60 hull, the thing for you to do is go back and look at the Series 60 model test charts, because now you just have a mathematical expansion of the hull you've already done. It's you're reusing somebody else's model test, which is the highest precision, in a lower order method. So just keep that in mind. Now, when we shift over to propellers, the 1D, 2D, 3D, we describe propeller geometry with similar parameters. We will have a parent propeller that has a single pitch that we might describe a diameter, a blade area ratio, a blade count. These are individual numbers. And we'll use empirical statistical equations or polynomials of the charts for things like B series, GON, Newton Rayder, SK, all the very well-known propeller series that we have. And when we talk about design or optimization, what we can do is solve for some of the parameters of proper diameter, pitch, blade area. NavCad is the tool for this 1D parameter-based analysis. As we go up in order, we'll use a blade element code where we'll take our propeller and cut slices through it. And so we'll integrate those slices radially from the root up to tip. And we can put a representative foil on each slice and think of it as kind of the bounding box. So we're integrating a set of foil characteristics radially. And so we can get an optimized pitch and camber. We can do strength checks and cavitation checks. So it gets an order of magnitude much higher than a parametric method, and it can be used for much greater detail and precision. And that's our prop elements code. And then true surface base, panelized 3D surfaces, CFD, of course, full wake field. There's a variety of different analytical methods, RANDS being probably the most popular of it. But when we talk about design, it's typically coupled with an external solver. So you'll use a tool like Mode Frontier or Casis or something like that to drive the CFD analysis to actually solve for an optimization in this. So those were the established methods, giving you a sort of a playing field of the 1D, 2D, 3D kind of characteristics. Now let's talk about the use of lower order codes before CFD for what we call design space optimization. And our objectives of using a lower order analysis is to reduce the amount of CFD that's necessary, to reuse CFD results that already have been done, or potentially omit the need for CFD altogether. And so we'll talk about component optimization, if the CFD is really needed for the business objectives, how to reduce demands on CFD resources, establishing benchmarks, and lower order methods for the system design space optimization. Now, I'd like to just take a moment here and talk about optimization in general. CFD and many of these codes require a convergence to an answer. And it's probably fair to say that they never reach zero true convergence. They always, you have to select a window within which your answers are stable enough for a period of time that you can say, yeah, that's close enough to be my answer. And so many of these convergence metrics look like a sine wave of declining amplitude. Well, if you have different designs in a design space, just take a propeller and you're trying to find the right pitch, and you have this big matrix of different pitch values that you're investigating, you might in fact have the humps and hollows of the convergence that are not in sync with each other, that may be offset a little bit. So depending on your convergence outcome, where if we waited long enough, we'd see that blue was lower than red, if you chose incorrectly and picked a point here, for example, you get an incorrect answer of red being lower than blue. So you'll want to understand the code, you'll want to understand the behavior of the convergence so that you can truly pick out the qualitative relationships of the outcomes. Now, lower order deals with this larger uncertainty, larger changes, and says, okay, I'm close enough here to get me in the neighborhood, and then I'll deal with CFD, on the upper ends of this. Lower order tools generally have no convergence issues like this because they don't have an iterative process. They seek a singular answer. Now, optimum and optimization, I used to teach an intro to naval architecture class, and it's great to watch students struggle with this concept of optimization because they think there's one perfect answer to everything. So they're looking for the peak of everything. And yet there's this huge broad gray area of acceptable solutions that are within 0.5%. And when we as naval architects recognize that we're juggling not only hydrodynamic performance, but structure and loading and cargo, and we have a business mission because we're designing a box ship that we need 200 meters of parallel mid-body that's wall-sided with a flat bottom, hydrodynamics is secondary to all of that. So we have to keep in mind what a rational decision for optimization really is. Within the framework of lower order tools, we can begin to look at component optimization because, as I said, even within the context of the system, a better component, once the system is satisfied, is going to give you better outcomes. In our NavCad software, we have what we call a minimum drag utility. It's a simple duty profile, effective power, kind of a weighted energy analysis that takes the principal parameters. And instead of telling you this is an optimum, it gives you a measure of if you can move longitudinal center of buoyancy forward, drag is going to be reduced. If you can put a bulb on this, drag will be reduced. If you can put more transom immersion in this, drag will be reduced. So you as the engineer and the designer have to make those decisions about whether you can do that or not in the context of everything else in the design spiral. But lower order tools allow you to very quickly see and understand the big picture improvements that you can make early on when you're allowing the design to mature. And when we talk about propellers, a simple propeller matching, Hull-Propeller-Drive-Engine systems, the parameters that we optimize are the gear ratio or shaft RPM, our blade area ratio, diameter, and pitch. The big parameters of a propeller design, because this gives us what kind of a gearbox do I need with a particular engine model. This gives us what kind of aperture size do I need and tip clearance, characteristics of my stern. Am I looking at 4 blades versus 5 maybe for hydroacoustic purposes? And we optimize for load matching, maximum efficiency, and we can even apply a cavitation constraint in this. Now, one of the questions that we want to answer is CFD even needed in this? And with the Series 60 example that I gave, if you were designing a truly B-Series propeller, perhaps not. Now, what's the purpose of the calculation? Is it speed and power? Well, speed and power predictions can be achieved very faithfully and very reliably with lower order methods in many cases, and even fair to say most cases. Propeller design, which is a geometric design, I can achieve much the same with lower order tools as well. But if I'm interested in visualization, if I'm interested in interrelationships, hydroacoustic pressure pulses between propeller blades and hull surfaces, I may in fact truly need the higher order codes of this. So understand the problem first, and then the order of the code will naturally lend itself to that. This last point, it is changing to a certain extent, but I still believe it's true that for successful outcomes, CFD typically requires a collaboration between the design subject matter expert, the naval architects, and the CFD specialist, the subject matter expert in the codes. That lower order tools, of course, does not. But we're seeing more and more software tools trying to create wizards and front ends to help guide practitioners as opposed to specialists be successful with that. And I applaud that, but I still look at it with a certain amount of care. Are lower order options sufficient? Can we get sufficient fidelity? And like we talked about, speed and power, propeller design, and visualization. Now, this plot here is interesting because when we talk about benchmarks, and we'll talk about how lower order tools can provide benchmarks for higher order tools, we can use a variety of different benchmark options. The end of this game is a reliable prediction of a performance. Somebody's going to spend a lot of money buying an engine and building a propeller for this ship. So we need to make sure that our numbers are reasonable. Well, in our software, we spend a lot of time on this idea of a prediction confidence. We have these things called confidence plots, which reflect kind of a minimum Pareto line. This green dashed line here is kind of a minimum line below which you must consider things are optimistic. And this is kind of the best of the best. We took huge collections of model tests with different hull categories, merchant ships, tugs and trawlers, go-fast boats and things. We basically took the bottom of all the curves and said, if your prediction is coming out below this, you really need to think about it. And so that's one benchmark. And there's also these little markers here that we call benchmark vessels that you can enter in simple characteristics of a sea trial or a boat test that you've done, and it scales using fruit scaling and kind of a clever kind of power relationship scaling. It will scale a benchmark vessel to the size of the ship that you're analyzing, and plug those points in at proper speed and proper power. So you can use similar but different sized vessels as a benchmark for your analysis as well. Now, we're all going to CFD, we're all using CFD, so how can I make it more efficient? How can I use my CFD assets as effectively as possible? That's where this initial design space optimization comes in. Out of all the possibilities, the huge matrix of the different hull parameters I might investigate, I want to narrow myself into a corner or into a space where I know I'm going to be reasonably close. And that's this idea of design space optimization. And so we can use lower order tools for hull shape or propeller parameters to get us much closer in the neighborhood before we flip the switch on CFD. I mentioned reusing CFD results. We can also use lower order tools to create predictions for initial starting conditions. This doesn't always provide a lot of benefit, but in some cases it can. With the prediction of sink engine trim that we have in the codes, you can actually create a starting point so your CFD has to hunt initially, has to work less hard in order to get to its point of convergence. And again, the benchmarks for assessment. Now, there's a difference between validations and benchmarks. Validations prove a process, and benchmarks suggest the answer before you've actually run the calculation. So you know kind of where your answers are going to be. And disparities from benchmarks point out possible errors in the models, in the data models, whether your gridding is incorrect or not, or the prediction models, turbulence settings, whatever it may be. You don't really know necessarily what the issues are. But I want to give you an example of one right here. This was a project we worked on last year that we were a sort of a specialist brought in to help a naval architectural company that was doing a maneuvering study. And the owners, a Coast Guard, demanded CFD analysis on this. So the naval architect engaged a major classification society to do the CFD work on this. And as a part of their report, they presented an open water KTKQ curve of how they had set up the model of the propeller. Now, there wasn't any comparison to a baseline. It said, here's the KTKQ curve. And my immediate reaction was, is it correct? Is it right? Is it relevant? Is what? So we did our own studies using the lower order curves for the same propeller, and we came up with very different answers. First, this was a propeller that was kind of similar to a B series, so we used the lowest order 1D calculations to kind of give us a sense, and then we used our 2D prop elements to do a detailed radial distribution of the foil shapes and the propeller, and our numbers were this small dash line, and the original numbers were the dark lines. As you can see, the KT, the thrust, pretty close. The KQ, they greatly over-predicted. And we brought this to the attention of the naval architects, the owners of CFD companies, big brouhaha, big discussion, like, why was this? You know, they had never checked their prediction against any benchmarks until we brought it up. Well, what we found was that the CF tool that they were using did not spline the foils on the blades properly. It instead created a polyline faceted geometry of a whole bunch of flat panels. And so right at the nose, you had this little triangular nose on things. So it's no wonder that the drag of that foil was as bad as it was. And once they flipped the proper setting to spline it instead of using a polyline, everything fell into place and it was fine. But they had wasted 2 weeks of CFD runs that they had to throw out, but we saved them from, you know, any further errors on that. So if they had followed a proper benchmarking process, they would have found that right away. This case study was for a RoPax project, and I have to put this slide up here because we're required by the agreements of the project to tell you that it was sponsored by the European Union and all these other things. Great people to work with, I have to say. This has been a fabulous project. And so we were working with a Greek company, NAP Engineering, for Blue Star ferries on 145-meter RoPax, where the owner came down with this mandate to reduce the carbon footprint. It was very nebulous, which, you know, for designers, that's great because it allows us to actually think and try to be creative about things. But our tasks in this were to look for drag reductions, first be able to do the prediction of the drag, look for drag reduction opportunities, to do a prediction of CO2 production, because that's going to be the benchmark on this when they're talking about a carbon footprint. That means CO2 production. And we were to look at this with dual fuel engines with LNG as an option, and to assess this across an entire operating profile where we're looking at total fuel consumption and total CO2 production across the entire voyage. And this was a preparatory development for the award of the contract to the naval architect, and they were successful with this work at obtaining the award. So we're getting set for kind of a next phase, which would incorporate our two-dimensional work with CFD in order to refine this even further. Now, we use the ADVM method in NavCad for this, the sectional area curve distribution, and this really is just a little summary of some of the characteristics in this, but it's not just a linear code. Our brand at Hydrocomp is really about quantitative fidelity. Again, people are going to spend a lot of money buying equipment based on predictions that we make. So we need to make sure that the total resistance, which includes all the viscous, form factor, hump hollow interaction, boundary layers, all of that are represented in the method. And what we found is that through our validation, that this is broadly applicable, but it's not suitable for all things. Barge forms would not work with this. Interestingly, very shallow hulls like a sailing boat scow would not be suitable for it as well. It tends to overpredict significantly. So we looked for a validation study. to prove that the method was suitable for a vessel of this type. And one hull that's used frequently for CFD and flow code analysis is the Creso container ship, the KCS. And it looks very similar to the hull that we have. It has a bulb, it has similar length over beam, similar midship section, similar prismatic coefficients, et cetera, et cetera. And this is the outcome of the curve. The brown line is the model test, and the blue line is our prediction of that. And so it matched the curve shapes well, and it was somewhat conservative. So qualitatively, it was excellent, and it was a little conservative. So we felt that the ADVM method was going to be suitable for that. So we started to look at the hull itself, and the design was interesting. It was basically a shorter vessel that the owner mandated just to put kind of a tail onto a volume in order to get more lane space for the trucks. And it resulted in a sectional area curve that looked like this, very flat. There was this inflection in curvature. And we speculated that was probably a candidate for modification. So we took a very simple smoothing of the geometry and we put it through the ADVM method. And because of the nature of the linear wavemaking code that we used, we were able to kind of integrate it in an inverse way and look at what longitudinal space of the ship really contributed most to resistance. And so what we found was that just upstream of this inflection, we got a big wave-making hump. And we did a study with 2D foil codes just to make sense that wave-making or that influence upstream like this made sense, and it does. And by smoothing this out, just a little bit of modification in the smoothing of the stern, we dropped the wave-making drag significantly from this arrow point to the lower arrow point here. And once we did that, then we incorporated that into the system analysis. That allowed us to use a slightly smaller engine model with a dual fuel variant. So the original hull with the original marine diesel oil engines against the proposed modified hull with the small stern improvement with MDO and LNG, when we're all said and done, we're looking at 3,100 tons reduction in CO2 production for one ship over the course of a year. And that was pretty significant. So we were really, really pleased with that outcome. This was an interesting design space optimization project, and probably more of the classical design space study that you might expect, where we're looking at a variety of hull form variants, and then which is the best one of this. Now, this was an EPA research vessel up in the Great Lakes, and they came to us with a mandate and a mission to make our boat green. It was like, you're the EPA, and they recognized that this was an old hull. They wanted to do something with it. And so it was like, well, can we add a bulbous bow? Like, sure. Is it going to work? Well, maybe. Let's look. And so they gave us a CAD model, engine specs, mission profile, and the shipyard we were working with wanted to make sure that this was going to be simple because the EPA didn't have a big budget for this. So we were constrained by manufacturing requirements of really just a cylinder, a hemisphere, and a fairing. And so the limited amount of parameters that we had was quite small. We had a diameter, we had a nose extension from the forward point of the water plane, and a vertical center. So basically, we were trying to solve for three variables in a cylinder hemisphere orientation. And so it had to be a system level solution because what we were after was fuel consumption improvements. So we had to take this all the way through. Hull-Propeller-Drive-Engine had to be cost effective because they didn't have a budget for anything else. And so they didn't want to study this to death. They needed a lower order solution for this. We did have a discussion about CFD for validation, and that was in the cards. And it needed to be quantitatively accurate, and the schedule was tight, so we had to be able to produce this quickly. So this is basically the hull shape that we had with one of the representative cylinder hemisphere bulbs in front of it. And the hull geometry was developed first in CAD. The longitudinal distribution of section area, water plane, and the immersed volume of the section was brought into a table in Excel. And Excel then mathematically modified those for the different hull or bulb parameters, the cylinder volumes and wetted surface, the hemisphere volumes and wetted surface, changes in longitudinal center of buoyancy, etc. And this longitudinal distribution that we could then use within that ADVM method, the 2D method inside of NavCad. Well, first we needed to determine whether the ADVM was going to be suitable for this kind of a hull form or not. So we used our own 1D methods, which we knew were valid for that particular hull type. They were built for that kind of hull. And we had a nice tight fit on the resistance curve. So quantitatively, we were satisfied that it was suitable. And now qualitatively, we wanted to begin and look at, as I change my bow, so it has now a volume, a wetted surface, and an immersion of the volume that represented the addition of the bulb. What did that affect on outcomes? Now, we did this driven completely by Excel. In this particular case, NavCad was just a silent calculation solver. Excel was creating data, coupling to NavCad, sending data to it, letting NavCad in a quiet mode generate results, return those results back to Excel. And if, bear with me a moment here. This is a short, just a couple minute video on the process that we actually used. There's this first page to actually create the connection between Excel and NavCad to make sure that there's an uninterrupted data stream establishing where the files need to go. When NavCad actually runs, this little window that you see pops up. And when we hit the execute button, it went through the matrix that we set up on the first page of Excel for all the different variants of the bulbs that we wanted. Excel modified the sectional area curve for the different bulb parameters, the diameter, the nose extension, and the vertical immersion. And we're using a simplified weighted effective power using a duty profile that they had described for us. And effective power is a pretty good weighting because it is a simple analog for the overall energy that's needed to be used. Resistance is specific to a speed where power is a better way to communicate energy. So we used effective power here, and I skipped a bunch of this. I think this whole thing took about 6 or 7 minutes to run. I forget how many different variants of this, but this will be finishing here in just a moment. In fact, I can advance this. So what we ultimately found was in Excel, it communicated with NavCad, it created the variants, the design space, it sent each variant to NavCad for analysis. NavCad returned the results. Excel pushed it into a column, plotted a bar graph, and then we as designers could quickly inspect the bar graph and find out where our optimum design space is. They used a simple framing system to add this. It was completely external to the watertight integrity of the hull. They decided that they didn't have time for any additional CFD. They were just going to go with what they had, and they used what they called an orange peel approach for creating the hemisphere itself. And if you can see, somebody very cleverly put a big happy face on on the front of that. They ran some operational trials. This data is anecdotal, not as good as the engineer and me would have liked, but they did show a measurable fuel reduction with the system that they had in there for fuel rate measurement. You can see the blue curve without the bulb, the red with the new bulb, and they had an additional benefit of improved motions. Great Lakes have very short, steep waves. This was an additional benefit to that. So everybody wildly happy, big parties, champagne around. It was a successful refit on the whole project, all completely done with the lower order codes. Now this is really interesting. This was a project that we did with a company called Friendship Systems, who produces a tool called CASIS, and it was a design space optimization for a submarine type vehicle. And in the same way that we just saw Excel connecting with NavCad, CASIS as a third-party tool connects with NavCad. Now it's an optimizing platform, so it was responsible for all of the CAD work, all of the geometry, all of the optimization strategies, whether it's a design of experiments approach, or whether it was more of kind of a genetic algorithm solution towards optimization. It handled all of that. Now the optimizing function for this was improved battery life, maximum battery life, which we then translated to a minimum weighted power demand. And so it had to be a system, again, resistance plus propulsion. So we used NavCad's lower order propeller and RPM optimization as a part of this. So we solved for the geometry of the hull that gave the lowest resistance. And then we had our own method for predicting the hull propulsor. We have a 1D parametric method for predicting the hull propulsor interaction coefficients, wake fraction and the like, for the stern and the propeller, given the characteristics of these three sections: a nose, or a forward, a mid, and an aft tail. So it truly was a completely integrated propulsion, hull propulsor drive model on this. And because it generated results so quickly, we could do hundreds of variants on this. And this was kind of what the CASIS session typically looks like, that you can retain graphics and outcome and plots and things of the different geometries. And it had parametric relationships for what each of those sections looked like. So this wasn't a CAD file that just got stretched and morphed. You actually created algorithms, geometric shape algorithms, to describe how you wanted CASIS to manipulate that geometry. And an AUV is a great way to describe the process for that. And what we found was that for the 4-knot case, that the larger diameter, shorter vehicles proved to be substantially superior to longer, narrower. Now, from a straight resistance standpoint, they might not have been, but because our propeller design constraint was that we allowed the propeller diameter to grow to within the limits of the body diameter, within a margin of that, we got so much better on the propulsor side that we could give up certain resistance losses because our system is better. And again, it was an overall duty profile kind of based approach to things. So just as in summary of what we have described and talked about here today, is that lower order tools are, for me, are not only important, but absolutely critical and crucial to successful design, because the important work is done early in the design, in those stages where we don't know enough about the ship or the propulsor to really justify higher order codes. But when we get to that point that we do, we will have set the table with the 1D and 2D methods, so we can have benchmarks to know what successful outcomes from CFD are going to be, that we've narrowed the design space so we're only dealing in the neighborhood that we know we're going to find our best design, that we can couple that with things like Excel or other solvers to very quickly achieve those things. And we can find ways to use CFD more effectively by reusing analysis results, or even finding ways to start CFD closer to the final answer to improve convergence. But this idea of confidence really is the underlying theme of all of this. The end of the game is we need to have a confident prediction, and we're going to use all the tools that are available to us, from simple charts to higher order codes to model testing to C trials. And the lower order codes is an absolutely important piece to that puzzle leading up to successful use of CFD. With that, I thank you all. Happy to answer any questions, and I'll put this reference information up here. If anybody on the webinar side of things has questions that they want to reach out to me about, my email address is here. I'm always happy to chat about this stuff. And so right now we can take some time for additional discussion from the floor.